Hey, yeah, so today I'm going to be talking about how Chainlink Labs aims to solve the Oracle problem, what the Oracle problem is, and a couple of institutional cases for how we can interact with off-chain data on-chain. Awesome. So when we talk about the Oracle problem, we're effectively talking about the fact that blockchains are disconnected from the outside world. The problem itself is the fact that blockchains are complete state machines and have no access to external data. They're completely isolated networks akin to a air-gapped computer or a trusted execution environment. And how we bridge the connection between them is effectively with a separate piece of infrastructure. And that is an oracle. So Alan Turing sort of came up with this concept of oracle machines as super Turing machines, that they're machines encompassing a classic Turing machine connected to some sort of black box. This abstract entity that's capable of solving some problem, which may be a decision problem, a functional problem. It's effectively just a solution that can produce it's effectively just something that can produce a solution for any computational problem we throw at it. So why don't we just connect each node to the same API? As we mentioned, blockchains are state machines. They're inherently deterministic. Each node within the network would have to find the same result at the given time. And within software development, connecting to any external source doesn't mean that you'll have a deterministic outcome. So if we replay the same transaction, we should end up with the same state. So if we used to query a node, if we used to query an API independently, the data would differ between the nodes. So node A could say the price is $5, node B could say the price is $6. So when we consider validating the price in a smart contract, if two different nodes submit two different prices, it becomes really quite hard to solve. Centralized oracles sort of introduce a single point of failure. They become trusted, and the purpose of smart contracts is to achieve determinism by sort of forcing it through technology, rather than relying on humans or trust, effectively. So if this to be effective, the blockchain and its oracle must remain free from any single point of failure. The centralized oracle sort of controls the inputs and determines the outcomes. If you're securing billions worth of value, you can effectively change the price to whatever you want to basically create loads of different outcomes that could be very advantageous for you. So Chainlink tries to solve this by creating a decentralized oracle network. So overcoming this problem means that we need decentralization to prevent data manipulation, inaccuracy, downtime, and loads of other different things. So a decentralized oracle network, or we call it DON for short, combines multiple different independent oracles, node providers, different data sources to establish basically end-to-end decentralization. So how we do this is by having high-quality code and also hyper-reliable Oracle node operators. So institutions around the world run these different nodes for us, and we effectively partner with them to solve a number of different problems. So a lot of the logic that underpins this is something called OCR. It's the off-chain reporting plugin that we effectively have. It was written by our research team. We've got a couple of papers published on it. And it allows nodes to aggregate their individual observations off-chain into a single report using a secure peer-to-peer network. A single node submits a transaction with the aggregated report to chain, and each report consists of many different observations and has to be signed by a quorum of nodes. These signatures are verified and then posted on chain. So OCR itself was quite a weird and complex protocol that effectively combines the benefits of peer-to-peer networking with also the security of just static cryptography. So we effectively elect a leader, and the leader will go around and ask all of the different nodes within the network for observations. Those observations are something that it would see. So for example, in the context of data feeds, where we want to find a price for an asset, we will ask each node what the price for that asset is. We'll effectively aggregate them together. The nodes will sign the data, and then we go into effectively the report stage. So the leader then generates the report. The other nodes also try and generate the same report. And then we need a consensus of nodes to come to agreement that this report is correct. OCR in the actual protocol itself does allow multiple reports. So theoretically, you could have two conflicting reports at a given time. But within the actual code itself, you can modify this to be a single report. So this sort of happens, as I've mentioned, in a couple of different phases. So this is just a lovely little GIF that I did not make myself. that basically describes how OCR works. So the nodes fetch this data, they sign it, they put it on chain from various different data providers and the nodes, and we effectively create a median of these values. These medians across the node are then medianed again to get an accurate price for a realistic price of what various different data providers could see what the actual price of the asset is. So I think a question previously when we talked about if one exchange has a really high price and another exchange has a different price, you can use market weighted volume and things like that to be able to basically say that this exchange that has the vast majority of the volume going through it should be a higher percentage of the actual value. So OCR itself is BFT tolerant. So the Byzantine's general problem is a very fun and interesting problem where effectively we need a majority of the generals within this like theoretical problem to attack the castle at the same time. So effectively, we just need a quorum. So OCR protocol itself defines a couple of different configurations. Research paper lays out that we should have 3F, F being the number of faults or malicious nodes, plus 1. So that's the sort of guiding principle for it. So you can have like 10, 16, 31. And then the quorum of the minimum responses required is effectively just 2F plus 1. So yeah, just a bit of an overview of all of our different products. Like at the top, we've got CCIP, which is how we move data across different chains. Like if you have all of these different state machines, you sort of want to be able to get data across different machines. That's where CCIP comes in. Then we have our data stack, which is data streams, data feeds, virtual reserves, and then the off-chain computation. So we have functions, automation, VRF. And this is, yeah, all powered by Sybil-resistant code and security-reviewed node operators. So I guess we'll get into what data is. So just a bit of a case study. In 2020, there was a massive liquidation on Compound due to an error in the DAI stablecoin. This was supplied by Coinbase. Well, the data was supplied by Coinbase. And data from TradingView showed that DAI dollar peg on Coinbase climbed to $1.34, which is a 34% premium on the actual value of the stablecoin. Inspection of DAI price across the market showed that the issue occurred only on Coinbase. So due to the incorrect price feed from Coinbase Oracle, some users became under-collateralized, and based on the baked-in protocol rules, that meant a forced liquidation of a huge amount of positions. So as you can imagine, there was a numerous flash loan attempts from different arbitrage plots that ended up scouring the market with loads of different opportunities. And yeah, like one of the biggest losers in this lost $49 million in the process. So yeah, so we talked a bit about having different layers of decentralization and how you get this high quality data. So we have data from all different exchanges going from different data providers. These chain nodes then listen to various different data providers and create a median of these values. We effectively sign these reports and then publish the data on chain, and then dApps or user contracts can then interact with them. So we have 3 different layers of data aggregation. So we don't have a single point of failure, and we aim to sort of do a defense in depth sort of methodology. So you have this like raw data from different exchanges. It doesn't necessarily have to be an exchange, it could just be some sort of data provider. You also have data provider aggregators as well that try and take data from various different sources. And then the node operators will listen to different sources of data, and then we aggregate the results together and then put them on chain. So we have 2 different methodologies. We have data feeds and data streams. Data feeds is the traditional one where you imagine an on-chain value needs a price for something. So off-chain, we collate this data from different providers, we put it on chain, and then dApps, DEXs can all listen to this data. Now, for lower latency data, because as you can imagine, it's quite expensive to put data on chain with a very high frequency, especially given how much the stock market can change for various different things. This is where data streams comes in. So data streams is a lower latency model of it, which still provides the cryptographic proof that you can verify any data that comes out of the API on chain. So effectively, if you're trying to interact with this data, as long as you pass in the attestation on chain, you can ensure that the price is correct at that time. So yeah, as we sort of mentioned, data feeds optimizes this on-chain delivery. Like you can just query the contract and you get the latest value at that time. If the price changes significantly as well, you can see the value on chain as Dom will also produce in a report. Data streams is for bigger granularity of prices. So as it's lower latency, we're able to stream it via an API. It's cryptographically verifiable via the report we're done. So proof of reserves is a bit of an interesting product. It provides cryptographic truth for any underlying collateral for any on-chain asset or off-chain asset. So you can imagine that a bank is issuing stablecoin. They want to be able to prove that any token that they mint on chain is actually backed and insured on chain. So as you can imagine, this is pretty important for regulation and loads of different things like that. And you also run into these different situations where you sort of want something like proof of reserves. So you can have a trusted custodian that interacts with the proof of reserves contracts. And if I want to ensure that I mint 100 USD on Avalanche, for example, I have that 100 USD backed in physical assets. Now, if my contract got hacked, for example, I can prevent an infinite mint with proof of reserves by ensuring that I never mint more than the actual collateralized asset I have on chain, off chain, sorry. So as you can see, we've got a couple of different examples of like when code errors and people not implementing protocols correctly can become really important. So Wormhole, the cryptocurrency platform, is also a bridge, was hacked for 325 million after a GitHub error. The security flaw was fixed, but it wasn't applied to the actual live code. Someone spotted it on GitHub and then drained 325 million US dollars from the protocol. Attack meant $569 million worth of BNB tokens in the bridge exploit. And Qubit suffered a similar loss as well. So you could also do something like a cross-chain proof of reserve, where if I want to mint on one chain, but I want to ensure that I have collateral on another chain to support a weird, complex transaction in a more like banking scenario, like a DBP scenario, something like that. You can have tokens on a different chain, and the on-chain reserves can do a balance check, and you can obtain collateralization on any asset. The deviation triggers on-chain transaction updates, and then the dApps can effectively use this code to ensure that the reserves on-chain. So if an asset becomes under-collateralized, we have a transaction failure. If it becomes over-collateralized, we can do the thing we want to do. So you can do an off-chain proof of reserve as well, where an institution holds this value for us. You effectively have to trust the institution, which is, depending on how you view sort of Web3 space, might not be something that you want to do. So the off-chain reserves do this balance check, and we can obtain the collateralization, and then a similar thing, exact same thing happens. So it's pretty critical infrastructure for some tokenized assets. Like you could have a crypto fund that has reserves for an asset. You can have a real-time auditor that interacts with the Chainlink network, and then we post these things on chain. You can do shares or fractionalized token minting events and just ensure that you don't under-collateralize or over-mint. The product I work on, so I'm a lot more familiar with this. So when you're thinking about blockchains, you have these two different models. We have this siloed approach where each private chain, because some banks might want to launch private chains, and public chains aren't able to interact with each other. So to effectively have USD or USDC on one chain and another, if I want to interact with a contract on another chain, but I don't have the tokens on that, I need to be able to send them across. Otherwise it becomes an absolute pain, and you might have to just like walk up to someone and just ask them, if I give you this money in cash, can you just send me USDC on a different chain? It doesn't really work. So security and reliability are core principles when it comes to cross-chain connectivity. So $2.8 billion was lost in cross-chain exploits. Ronin Bridge was famously hacked for $625 million. And like the Neo Protocol exploit as well, there's a ton of things that could go wrong. So the cross-chain stack itself resolves around different things. So apps and wallets, the DeFi space, NFTs and gamers. And then CCIP comes in by having a separate network built in a completely different language called RMN. We'll get into that in a bit more. We support programmable token transfers. And yeah, we use OCR2 and OCR3 for consensus. So CCIP is built on this idea where the more decentralized the model, the more secure it is. So you can have this like first level approach where you just have a single node, a single centralized operator. Then you could say, well, actually, I'm sort of decentralized and I can have multiple nodes, but still with a centralized operator. Level 3 takes it up a notch where you still have a single network where you can have multiple nodes, multiple operators, but you still only do one thing. CCIP comes in where we have various different networks. We have the commit network, the RMN network, and the executing DOM. They're all separate decentralized networks, and they all work together to be able to validate data. So yeah, we have a single and simple interface that connects dApps to various different blockchains. So the router contract provides a fixed input across all chains. And you could send tokens, data, or programmable token transfers, which is just a fancy word of saying doing both at the same time. So a bit of a deeper look into the architecture of how CCIP works. We have the router contract, which can then interact with the on-ramp. The on-ramp can do various different things, but effectively, if you're sending tokens, it will just look in the token registry, go to the token pool, which could be configured to lock, or it could be configured to burn the token, depending on how you want to do. We then have a separate network called RMN, or the Risk Management Network. One thing that we explored early into the design of CCIP was this idea of a supply chain attack, where one party could effectively inject a vulnerability into a package that we use. So CCIP is primarily Risk and Go, and then Solidity for the on-chain contracts. But we had a separate code base built by a completely separate team in a different language to sort of reduce this idea that if someone was able to inject a vulnerability into CCIP through the supply chain, we should be secure because we have a completely separate network. This is sort of amped up slightly as well with the different decentralized networks that we have, so the commit DOM and the executing DOM. The commit DOM effectively generates Merkle roots from the on-chain, from the values of the source chain. We basically attest that they've reached finality, and then on the destination chain, we put one to the commit store. So this is the architecture for 1.5. For 1.6, it's changed quite a bit. But effectively, this commit store acts as a proxy to the state that's happened on the source chain that is cryptographically verifiable. The executing DOM then looks at the data that's on the commit store and then effectively executes that and agrees that all nodes have seen that. And it can't just be a malicious RPC pretending that that data is actually on the destination chain. And then, yeah, for tokens and the rest of the contracts, it's the same thing, bit in reverse. So maintaining data across blockchains is surprisingly hard. If you launch a tokenized asset on one chain, but your users demand and the market demands that you have it on a different chain, keeping these two in sync is really hard, especially if you have multiple mint operations on these different chains. You can effectively over-collateralize and your price of your token comes spiraling down. We've seen this with a lot of exploits we've talked about previously, and this is why it's pretty secure. This is why it's pretty important we have a secure cross-chain approach. So a bit more into chain compute. So we talked about the idea that smart contracts can't automatically do stuff on their own. They need this external input because they are state machines. So Chainlink tries to solve this by creating a specialized version of our DOM. It provides a trust minimized way to trigger smart contracts based on predefined conditions that you've set. So imagine that you want to run some kind of function, similar to like a cron job that you'd want to run like every day, every week, every hour. You would be able to effectively post this data on chain and say that I want to do this item every hour. And then Chainlink can effectively just say that we will call your contracts every hour. We will ensure that, yeah. So yeah, the automation registry like manages these participants, rewards nodes for successful upkeeps. Developers register their upkeeps there, and you could sign up as a node operator for an automation node. The forwarder contract acts as a bridge between this registry and the user contract. We can provide data as well that could be executed at a given time as well, which is why we still use OCR off-chain. So you have these different triggers, which could be like time, log events, and you sort of have this like custom on-chain logic as well. So the smart contract itself does some logic. It offloads this to the off-chain DOM. You could sign a report containing the on-chain transaction details, call the upkeep contract, and then interact with the blockchain. So yeah, automation upkeeps are pretty interesting. You could define a specific or automated task or function that's executed by Chainlink that maintains the proper functioning or updates the state of the smart contract. These are monitored off-chain for predefined conditions or triggered that are monitored by a DOM in the check upkeep function, and when met, perform predetermined actions on behalf of a smart contract. So that's pretty much it. There are a couple of things else that we could briefly go over. So one project that was launched relatively recently at least, is this idea of Chainlink platform. Yeah, so we talked about this idea of a Chainlink runtime environment. So Chainlink sort of became the market leader for DeFi and TradFi smart contracts, and we have a pretty good security track record. We use CCIP is a widely used cross-chain standard. So we sort of saw this gap in the market where banks were typically still using COBOL, and then in the 1990s they transitioned to using Java, and then a lot of banks wanted to go on-chain as well. So the idea being that we could create a similar thing to Java, but just exactly on-chain. So you could do things like interact with HTTP, you could do off-chain consensus, and various different bits like that. So the conceptual model of this is we have these data APIs and messages. So you could write a workflow written in Go or TypeScript, which then gets compiled down to WebAssembly. And these different capabilities, like calling an API or running a workflow or transforming this data, and then you can effectively write to chain. So you can combine these ideas of like multiple chains, these Web2 systems, and put them all together. So the architecture is sort of split into these different sections where we have these data APIs. So you have the inbound API that can trigger capabilities, these workflows, which is like the CRA itself, and all of these different capabilities. So compute, you could send transactions, do a key value store, event store, policy store. So this could be useful for some banks and things like this. And then we have this idea of like reading from a chain and writing from a chain. So these different read-write implementations across all of these different chains are useful. So yeah, the Chainlink runtime environment just retrieves data from a smart contract. You could then execute an off-chain payment if you particularly wanted to, and then you could do confidential computation on that data. Yeah, so different payment systems, different APIs, do confidential compute, as we sort of mentioned, write to a chain, read from a chain. The idea being that this platform, you could design effectively anything that you wanted to do. I think that's pretty much it. I don't think I've got anything else and went through that way too quickly. But yeah, does anyone have any questions at all?
Thank you for doing. Any questions?
My question is like, how does Chainlink actually reduce the gas fee up to 90%?
Yeah, so the effective idea behind doing this is instead of, if you have a DOM of 16 nodes and you each get every single node to publish the transaction on chain, each of them pay a fixed cost. So like the 21,000 you do with like a standard ETH transfer, for example, each of those nodes have to pay a fixed cost for those transactions. So if you're able to combine all of those signatures off chain and then post them in a single transaction on chain, you can effectively reduce the overall cost that you're paying by combining it to a single transaction.
Yeah, but that's the ideal case scenario. Like right now, okay.
Because yeah, like this basically changes the dynamics when you have a bigger DOM size as well. Like if you have like 30 nodes, you have the public keys on chain, so you can validate all of this data in a single function call, rather than like combining this state together and then like aggregating these signatures on chain, which can be quite computationally expensive as well.
Kodey, can you explain the difference between how Chainlink protocols deliver data versus how we get it from Uniswap, which was mentioned earlier in the presentation?
Yeah, so Uniswap and some DeFi pools tend to do things slightly differently. I'm not too sure on the exact Uniswap implementation, but I'm pretty sure that they use liquidity pools under the hood to basically balance the price of the data on chain. So by filling the pool up in different like weighted sections, you can effectively ensure that when you create the pool at a given price, the pool remains balanced. So effectively, you can create a multiplier between the price of the assets. Maybe. I'm not entirely sure on how Uniswap works. I'm also not super sure on like our data infrastructure as well. I'm more focused on CCFP.
One question I have with regards to the cross-chain protocol. So that looks like you're trying to, what you're doing essentially is replacing any custom bridge implementation in terms of having some validators in between the two chains and signing the messages, right?
Yeah, so there's a couple different approaches that we sort of considered. So Layer 0 are another big competitor as well, where they have these on-chain layers, which they can aggregate data off-chain. Effectively, the difference that we wanted to do is we wanted to post the data on the destination chain first, have the nodes come to consensus on the values from the source, combine this into a sort of like Merkle tree, post this data on the commit, and then ensure all of the nodes see it. So we're effectively doing this consensus step multiple times throughout it. So effectively, if a single RPC got compromised, we still have security of the network. I don't know if that answers your question.
Yeah, makes sense. Mike, you referred to a lot of kind of attacks that can happen in the bridges. And initially you discussed proof of reserve. So I was a bit confused if you actually also provide some functionality that automatically does proof of reserves and could protect against I don't know, a programming error in solidity in one of the chains that maybe you have some arithmetic issues and instead of I don't know, doing a floor for the protocol, the users gets a bit more every time, so you can have such issues in bridging smart contract implementations. So does it come and connect with proof of reserves or now those are?
Yeah, so it's something that we're definitely exploring. They're currently at the moment two separate products. So if a user wanted to do that, they can implement it on their receiver contract and then effectively fail the transaction at that point as well. So then the tokens won't be minted.
Okay.
So you could do like these pre and post white hooks if that makes sense.
Kind of like invariants that are
exactly. Just like hard coded
satisfied with proofs that come from the validators of what is the state of the other chain and aggregate the results. Okay, makes sense. Okay. Any other questions? So another question is like, what is the, if you can share like the most highly utilized Chainlink product beyond price feeds?
Yeah, so it would actually be CCRP. CCRP is pretty widely used across like a lot of institutions as well. We're integrating with a lot of banks as well that might want to have a private chain to private chain banking operation. So effectively ensuring that like if HSBC wanted to interact with JP Morgan, they could securely by effectively ensuring that this decentralized DON and all these verifiers together can come together and effectively ensure that this transaction has happened. And they can effectively, just transfer liquidity between the two.
So is that kind of a Swift replacement?
Yeah, so
that is faster.
Yes, like we're working with Swift directly as well on a couple of projects. I think we've been working with them since like 2016 as well.
Okay, and the idea there is basically you don't need to wait for the central banks to actually perform the transactions, etc. And you can just verify what has happened in the state of one bank and in the state of the other, and then wait for like the settlement to happen.
Yeah, exactly. So yes, they could do like a delivery versus payment scenario where if they wanted to say that we'll send you these tokens, but we want cryptographic proof that this settlement has happened, you can pay us after this verifiable proof has happened.
Okay, we don't have any other questions. I guess What's next?
Well, next is our to meet up about finding a job in Web3, and we're expecting some sandwiches and beverages something in the next 5 minutes.
Nice.
We can start 3 again, so we have the long breaks. If we're working on 3 minutes, 3.
Yeah, we can take a break for a few days, and then there will be snacks, and I guess you can ask Kodey more like more like professional related questions. Maybe the